In vector calculus, a conservative vector field is a vector field that is the gradient of some function, known in this context as a scalar potential. Conservative vector fields have the property that the line integral is path-independent, i.e., the choice of integration path between any point and another does not change the result. Path independence of a line integral is equivalent to the vector field being conservative. A conservative vector field is also a rotational. In 3 dimensions, this means that it has vanishing curl. And a rotational vector field is necessarily conservative provided that the domain is simply connected. Conservative vector fields appear naturally in mechanics. They are vector fields representing forces of physical systems in which energy is conserved. For a conservative system, the work done in moving along a path in configuration space depends only on the endpoints of the path. So it is possible to define a potential energy independently of the path taken. Informal treatment. In a 2- and 3-dimensional space, there is an ambiguity in taking an integral between 2 points, as there are infinitely many paths between the 2 points. Apart from the straight line formed between the 2 points, one could choose a curved path of greater length as shown in the figure. Therefore, in general, the value of the integral depends on the path taken. However, in the special case of a conservative vector field, the value of the integral is independent of the path taken, which can be thought of as a large-scale cancellation of all elements which don't have a component along the straight line between the 2 points. To visualize this, imagine 2 people climbing a cliff. One decides to scale the cliff by going vertically up it, and the second decides to walk along a winding path that is longer in length than the height of the cliff, but at only a small angle to the horizontal. Although the 2 hikers have taken different routes to get up to the top of the cliff, at the top they will have both gained the same amount of gravitational potential energy. This is because a gravitational field is conservative. As an example of a non-conservative field, imagine pushing a box from one end of a room to another. Pushing the box in a straight line across the room requires noticeably less work against friction than along a curved path covering a greater distance. Intuitive explanation. M.C. Escher's painting Ascending and Descending illustrates a non-conservative vector field, impossibly made to appear to be the gradient of the varying height above ground as one moves along the staircase. It is rotational, in that one can keep getting higher or keep getting lower while going around in circles. It is non-conservative in that one can return to one's starting point while ascending more than one descends, or vice versa. On a real staircase, the height above the ground is a scalar potential field. If one returns to the same place, one goes upward exactly as much as one goes downward. Its gradient would be a conservative vector field, and is a rotational. The situation depicted in the painting is impossible. Definition. A vector field is said to be conservative if there exists a scalar field such that here denotes the gradient if, when the above equation holds, is called a scalar potential for. The fundamental theorem of vector calculus states that any vector field can be expressed as the sum of a conservative vector field and a solenoidal field. Path independence. A key property of a conservative vector field is that its integral along a path depends only on the endpoints of that path, not the particular route taken. Suppose that is a region of 3-dimensional space, and that is a rectifiable path in with start point and end point. If is a conservative vector field, then the gradient theorem states that this holds as a consequence of the chain rule in the fundamental theorem of calculus. An equivalent formulation of this is to say that for every closed loop C in S, the converse of this statement is also true. If the circulation of V around every closed loop in an open set S is 0, then V is a conservative vector field. A rotational vector fields. A vector field is said to be a rotational if its curl is 0. That is, if for this reason, such vector fields are sometimes referred to as curl-free field or curl-less vector fields. It is an identity of vector calculus that for any scalar field, Therefore, every conservative vector field is also an irrotational vector field, provided that is a simply connected region. The converse of this is true. Every irrotational vector field is also a conservative vector field. The above statement is not true if is not simply connected. Let be the usual three-dimensional space, except with the axis removed, that is. Now define a vector field by then exists and has zero curl at every point in, that is irrotational. However, the circulation of around the unit circle in the plane is equal to. Indeed, we note that in polar coordinates, so the integral over the unit circle is equal. Therefore does not have the path independence property discussed above, and is not conservative. In a simply connected region, an irrotational vector field has the path independence property. This can be seen by noting that in such a region an irrotational vector field is conservative, and conservative vector fields have the path independence property. The result can also be proved directly by using Stokes' theorem. In a connected region, any vector field which has the path independence property must also be irrotational. More abstractly, a conservative vector field is an exact one-form. That is, it is a one-form equal to the exterior derivative of some zero form. An irrotational vector field is a closed one-form. Since D2 equals 0, any exact form is closed, so any conservative vector field is irrotational. The domain is simply connected if and only if its first homology group is 0, which is equivalent to its first cohomology group being 0. The first RHAM cohomology group is 0 if and only if all closed one-forms are exact. Or rotational flows. The flow velocity of a fluid is a vector field, and the vorticity of the flow can be defined by a common alternative notation for vorticity is. If is irrotational with, then the flow is said to be an irrotational flow. The vorticity of an irrotational flow is 0. Kelvin's circulation theorem states that a fluid that is irrotational in an inviscid flow will remain irrotational. This result can be derived from the vorticity transport equation, obtained by taking the curl of the Navier-Stokes equations. For a two-dimensional flow, the vorticity acts as a measure of the local rotation of fluid elements. Note that the vorticity does not imply anything about the global behavior of a fluid. Conservative forces. If the vector field associated to a force is conservative, then the force is said to be a conservative force. The most prominent examples of conservative forces are the force of gravity and the electric force associated to an electrostatic field. According to Newton's law of gravitation, the gravitational force, acting on a mass, due to a mass which is a distance away, obeys the equation whereas the gravitational constant and is a unit vector pointing from towards. The force of gravity is conservative because, whereas the gravitational potential energy, for conservative forces, path independence can be interpreted to mean that the work done in going from a point to a point is independent of the path chosen, and that the work W done in going around a closed loop is 0. The total energy of a particle moving under the influence of conservative forces is conserved, in the sense that a loss of potential energy is converted to an equal quantity of kinetic energy or vice versa. Citations and sources. Citations: Marsden, Gerald, Tromba, Anthony. Vector Calculus. W. H. Friedman and Company. pp. 550–561. George B. Afken and Hans J. Weber, Mathematical Methods for Physicists, 6th edition, Elsevier Academic Press. Clancy, L.J., Aerodynamics, Section 7.11, Pickman Publishing Limited, London. ISBN 0-273-01120-0. Liepman, H. W., Roshko. 1957, Elements of Gas Dynamics, Courier Dover Publications, ISBN 0-486-41963-0, pp. 194–196. Sources: Atchison, J. Elementary Fluid Dynamics. Oxford University Press. ISBN 0198596790.